Okay, so this could be our first notes on the mole in chemistry. This could be a really important foundational set of notes. You want to make sure you ask questions and take these into your notebook and make sure you have these for reference later. This is going to really build on a lot of different concepts that we're going to learn about, such as empirical formula, molecular formula, many other things. So you want to make sure you're really paying attention and ask questions in class if you're not understanding something as we're moving along. So the mole is really, it's a unit. And this unit is used to help us keep track of atoms. And atoms are really small particles. Okay? This is really this small particle. But also because they're small, there's a lot of them. So if we try to imagine, how many atoms would fit inside of, like if we took the cap off of a water bottle and try to imagine how many atoms could fit in there, it would just be enormous, right? And that becomes a problem when you're in chemistry, when you're dealing with these very small things, these small particles, and how do we figure out actually how many there are? This mole was actually invented by a gentleman named Avogadro. That's just his last name. He has like 3 other names, but just remember his last name because they called this number that he came up with Avogadro's number. You can kind of see it there. And the thing we always want to remember, the really important thing to remember is that 1 mole is 6.02, and you can add another 2 in there if you want, 6.022 times 10 to the 23rd particles. So if we have like a mole of calcium, we have 6.02 times 10 to the 23rd atoms of calcium. And you probably saw in the video where they said if you have a mole of elephants, you have 6.02 times 10 to the 23rd elephants. A lot of elephants. And this number is huge, 23 zeros. Just add 6.02, just add 23 more zeros, and you get that number. It's huge. Okay? And it all comes back to the idea that atoms are really small. So this is Avogadro's number. And just remember, again, it's just a measurement. So treat it like a dozen, or I can't think off the top of my head of other units that we use, but a gallon, right? A gallon is another unit that we use. We could use, I don't know, lots of different things. But it's just a unit. So don't let this huge number scare you. You just have to remember kind of what it is. And then even if you can't remember what it is, you can write it down in your notebook, and the more you use it, the more it will become second nature to you to use it. The thing also to remember about the mole and this number of particles, it can be used with a single atom, like calcium, carbon, oxygen, any element or any atom, but it can also be molecules like sodium chloride, it could be O2 gas, it could be C6H12. 6, which is glucose. So if we're talking about a mole of these, there are 6.022 times 10 to the 23rd particles or atoms or molecules of NaCl. And then here, O2, we would have 6.02 times 10 to the 23rd molecules of O2. And if we had glucose, this right here, we would have 1 mole of them, we would have 6.02 times 10 to the 23rd molecules of glucose. So it can be used for a single element or an atom, but it can also be used for a molecule as well. So keep that in mind. And then when we think of molecules, and even with atoms as well, that this mole has some conversion factors that are pretty useful. And one of them is that not only is a mole equal to this many particles, it's also equal to the average atomic mass for any given element. So if we thought of like oxygen, and we just rounded oxygen up, we'd say the average atomic mass of oxygen is 6 AMU. So we could then realize that because the average atomic mass is equal to the mole, we could like make ourselves a conversion factor. I'm sorry, get the paper straight. And we could say something like 1 mole of oxygen. We could use a conversion factor and say it's equal to 16 grams of oxygen, like that. Or we could use another one. We could say 1 mole of oxygen is equal to 6.022 times 10 to the 23rd atoms of oxygen. We could also just use these. We could say 16 grams of oxygen is equal to 6.022. Or we could say 1 mole of oxygen is equal to, I think I actually said that one, but the 16 grams. But we could just go 16 grams equals 6.022. So lots of different things you can do with it. Lots of different conversion factors. And we'll look at that in class. Okay, so we can use mole to grams. We can use mole to particles. We can use gram to particles. So really you have those three. So if you're going to add these, we can have grams to particles. We can also have particles to moles. And we can also have moles to particles. So that gives us three conversion factors that we can use when we're presented with something. So here's an example. So you're going to always need your periodic table for these as well, so you might want to make sure you have that handy. And I'm going to show you that here in just a minute. So we have some problems here that we can solve using these conversion factors, and the idea that we know that 1 mole is equal to 6.022 times 10 to the 23rd particles or atoms or molecules. Okay. So this one says how many moles are in 5 grams of copper. So let me pause this, get my periodic table, and we'll start. Okay, so the question here is how many moles are in 5 grams of copper. So you take what you're given. This is going to be some dimensional analysis or factor label. And we write that as a fraction. 5 grams copper, Cu. And then we're going to want to end up with moles. And we're going to want to use a conversion factor that cancels out grams. And so if we want to cancel out grams here, we're going to look back. We can do grams to particles. We can do particles to moles. And we can do moles to particles. But here we really want to do grams to moles. And we don't see that one here, but that's another one we could use. And here, because we have grams on the top, we're going to want to put it on the bottom, grams of copper, and we're going to want to put 1 mole on the top. And I'll show you why in a minute. And to figure out how many grams in 1 mole of copper, again, we just look for the average atomic mass. So we get our periodic table, we find copper, it's right here. We're going to go like 2 decimals, 63.55. So you see that right there, you just use the average atomic mass, 63.55. Put that in there. And then we just do our math, right? So if we had a calculator, we would just do our math. But look here also as well, is that we cancel grams and we're left with moles. So that's how many moles. And we'll be able to calculate that. Let me grab my calculator. I'll pause again. Okay, so if I'm doing my math, it'd be 5 times 1 divided by 63.55. So I'm just going to do that math. 5 divided by 63.55. That's going to give me 0.078. We're just going to go 0.079 moles of copper. That would kind of give us our answer. So we only have 5. 1 mole is equal to 63, so it kind of makes sense. It's a pretty small number. We don't have a lot of moles. Very low number. So another example you might ask us is how many atoms are in the above sample of copper. So again, we would start with the same thing, 5 grams of copper. And we want to know how many atoms. We're going to use the same number on the bottom because we want to cancel the grams across. So we're going to go 63.55 grams of copper. And that's going to be, and then instead of using the mole on top, we want to know particles. And we can, because they're all the same, we can do, this one says, up here says grams to particles, but we can go the other way, particles to grams. So we know that we just put this number, 6.022 times 10 to the 23rd atoms of copper. Okay. And then again, we've canceled the grams of copper. And we just need to do 5 times this. And we would then do our math. So the way I recommend to do this is to kind of convert them into, scientific notation. There's a couple ways. I'm just going to show you how I would do it. I think it might be easier. So I would just take this as 5 times 10 to the 0. So then we just have 5. Because when you multiply numbers in scientific notation, you add the exponents. And we made this as 0, which is really just saying times 1. So we're just going to take the 5, you do the coefficients, and you add the exponents. So we do 5 times 6.022. Do that. And that gives us 30.11. And then I'm just going to do my division. I'll again make this times 10 to the 0. And again, if we were doing this in scientific notation, we would just subtract. But we made it 0, so we don't have to worry about it. So we're going to divide by 63.55. Do that. And then we get 0.4738. So we're going to go 0.474. And then we got times 10 to the 23rd. But we need to have something between 1 and 10 here. So we're going to move this decimal. I'm going to make this number larger. Good rule to remember, if you're making this larger, you make this smaller by the same amount. We move this one space. We made it one space larger, so this then becomes smaller. And that would tell us how many atoms of copper we would have. That's kind of how you do that one. The last one here, stop all the way, is, so how many moles are in 5 grams of copper 2 bromide? This one's a little bit more difficult, but it's not that different. So again, instead of having an element, just copper, now we have a compound. I'll show you how to solve that. What's going to be the mass of that? We do the same kind of thing we did here. And we're just going to go 5 grams of copper. We're just going to write it like this, bromide. This is copper 2, so it's going to be CuBr2. We have 5 grams of that. And just like we did on the top, we want to know grams of this, we want to do moles. So we're going to do grams of CuBr2 in 1 mole of CuBr2. And so then we just do our math. The thing we have to go in now is you have to figure out copper and bromine. Move this up here. So we got to do our copper and bromine. We just need our periodic table. We know what copper is. It's 63.55 grams per mole. And then we know bromine is, we look on our periodic table, right over here, 79.9 we're going to go with for that one. That's 79.9. Well, we know we have 2 of those, 2 bromines. So we times that by 2. Let's get our calculator out. 79.9, yep, times 2. That gives us 159.8. And we just add that to the 63.55. 223.35. 35, sorry. 35. So then we know what goes in here. So 223.35 grams of this equals 1 mole. Because it's just like the element. We just had one thing for the element up here. We just see its average atomic mass. But when we have a compound or molecule like this, we just add all the average atomic masses depending on how many there are, and that gives us how many grams per mole. Same thing we did with the last one. We would just do the math. So we would just take 5, we're ever divide it, it's going to be really small. Divided by 223.35. It's going to give us, 0.022. It's actually not that bad. 24 we're going to go with. We're going to double check our math on that one. I thought it might be a little smaller. 5 divided by 223.35. So we got. Okay. So then we would just, the answer is right. That's how many moles of copper 2-bromide we have. Okay. Then if we wanted to just turn this into particles, right? We could either start over and do 5 grams, and instead of doing the grams over 1, we could do it, 6.022 times 10 to the 23rd over this. But really, we could just take this, because we know for each mole there is 6.022 times 10 to the 23rd. So we just multiply this number by 6.022 times 10 to the 23rd, and that'll tell us how many atoms we have. Or how many, not atoms, how many molecules, how many copper bromides do we have. So if we just do the math here, 0.0224 times 6.022 is my exponent on this one. I might do this different way. Okay, sometimes it's hard to find them. So we're just going to take this times 10 to the 0. So 6.0 6.022 times 0.024. That gives us 0.13. 5 times 10 is going to be 0 plus 23, 23rd atoms of copper bromide. And we're just going to make this a number between 1. We move it, we make it bigger by 1. So we're going to make this smaller by 1. And that's our answer. So I showed you all the kind of examples how to do these. Let me know if you have any questions in class. We'll go over some tomorrow when you get in there. Make sure you have your periodic table. Make sure you kind of take these notes and get some examples for yourselves, and so you can look back at them if you're having trouble with them. This is kind of the beginning. This is going to give us the ability to do some other things with it, like figure out when we look at a bigger equation how much of each thing we have. So make sure you add these 2 notes. Sorry, these are a little bit long, but I did some calculations for you. Hopefully that's not too bad. And see you in class.